Okay, thanks so much. Okay, the vast majority of what I'm going to tell you about today is work that I have been doing over the last couple of years with two of my closest collaborators, Chi-Kwan Chan and Dimitris Psaltis, who was my advisor at the University of Arizona. And over the end, I will tell you about some current work that I'm doing with Jeremy. Okay, I know you have all thought about this problem in many different ways. I just thought I could give you my take and argue why is that modeling, stress modeling, or angular momentum transport modeling is more a matter of need than just a choice. Just to set the scale of the problem here, I'm plotting length scales on the horizontal axis and time scales in the vertical axis. And for the sake of the argument, I'm going to think out of 10 to the 7 solar mass black hole. When I say this, there are natural scales that show up in the problem. The inside of the event horizon, the broader region, just think about the region, if you go far away, this is no longer an accretion disk. Then a natural timescale in the problem is always a Hubble time. Hopefully we don't have to worry about such a long timescale. But there are several characteristics timescales that enter into a problem also very naturally. These are the orbital timescale, the saturation that we think about of the order of 100 orbits, how long it takes us to think that we have a realistic representation of the turbulence in the disk, and of course the viscous timescale that is a couple of orders of magnitude larger. So this is the region of parameter space where we think accretion disks live. And this is essentially what we can accomplish today, we can study today using numerical simulations. Okay? The question is, what are the natural phenomena? I will study accretion disks just for the sake that think that they are interesting phenomena, but it's also true that we are very interested in this for a astrophysical point of view. So what are the natural phenomena that we are interested in trying to understand? Well, these are all over the place. Essentially, black hole variability, I would argue, is more or less in this region of parameter space. Black hole growth is somewhere of longer timescales, and also if it is being fed from far away on larger length scales. And we can argue where to put the disk spectrum in the vertical axis, but you need to have an idea of the whole structure of the disk. So the point is that in order to cover all of the rest, we need to do something else, at least today. I would argue for some time. So the rest of my talk is going to be about mean field models of turbulent angular momentum transport. And this is not really something new, just the fact that we need models. In fact, we have been doing this for 35 years. And we have been writing this equation, arguing that the stress was the most important dynamical quantity in the disk, just set the simplest model that we can come up with. And with this, we have been calculating many different versions of the structure of the disk. And all of these details that you care about are sensitive to essentially the model that you use for the stress. So essentially what I'm going to argue is, we need to move a little bit forward with this. And it's not I'm trying to find a replacement for numerical simulations. I actually want to use numerical simulations, understand the turbulence better, and come up with a better model for turbulent angular momentum transport. So this is, broadly speaking, the goal of what I'm going to say. Okay, so this is not an explanation of how an alpha model works, but I thought it was a nice sketch. Essentially, given alpha, you set the stress. Somehow, I'm not going to go into the details. I don't claim that I understand how all of these processes, but you get dissipation. This is the temperature, the pressure fixed into the stress. This gets the height of the disk. So you see how things are related. So a key point here is that in order for us to calculate how these things happen, we need to give a value of alpha. And this is one of the main reasons we have been getting more and more refined with numerical simulations to get a very good handle on alpha, because essentially everything else depends on this. So this is a key point for us. So what I want to talk about is there a better way essentially to connect the MRI with all of this? So what I would call, I would say that the answer is yes, and this is what I would call an MRI disk. Essentially, I'm not going to worry about this part today. I'm going to forget about dissipation for a moment, but I want to see how do you actually generate stresses. What is the replacement for this? How we can actually forget about the dependence that we have with this link. And I would argue that a way to do this is try to come up with a mechanism that would do this self-consistently. Okay? And this is essentially what I want to do. It's a model for the upper part of this. Essentially, I want to use numerical simulations to constrain these type of models. Okay, so for these items, I don't think I have too strong about this, but we really need to move beyond alpha. We have used this for 35 years. It has been a very good model, but there are many standing issues that we are not going to solve within the framework of alpha viscosity. We know alpha is not constant, depends on many things. We know about numerical issues. We know about physical dependencies. Even if you believe in alpha viscosity, the physics, the problem at some point gives up. You can propagate information across sonic points. It should not happen, but the system of equations that you're using is diffusive. This happens in any case. There is no stability criterion when you use alpha models. We know that if it is MRI turbulence what is driving the angular momentum transport, it cannot be well represented for alpha viscosity. Alpha viscosity works always. No matter what is the sign of the shear, alpha viscosity will transport angular momentum. And this essentially, I will come back to this, but this boils down to the fact that MRI-driven turbulence does not behave like Newtonian shear viscosity. This is what we have been using for many, many years now. I think it's not a good model for MRI-driven turbulence. Okay, so just to give you an idea of motivating the type of model that I'm going to be talking about, this is a simulation, a model from a simulation from a code from Chick-Wan. So if you want to know the details, ask him. But the main point here is that you have an MRI unstable disk. There is shear, there is a vertical magnetic field. You are looking at this in Fourier space. And there is clearly a one wavelength that is growing the fastest. That's, of course, MRI instability. Then this is the stress power. Then after the statistic takes over, there is mode-to-mode interaction, other processes that are yet to be understood. But the power is in spectral space spreads out, and you end up with a well-defined spectrum. Okay? So the idea is, how can I use this to build a model for angular momentum transport? So schematically, I would like to think about this problem this way. It might be oversimplistic, but for the moment, bear with me for a second. So somehow, there is a preferential scale in which the MRI is pumping the turbulence, driving the turbulence. There are physical processes to be understood. Some of them we understand. There are things that we need to figure out yet. Parasitic instabilities, mode-to-mode interactions. This spreads the power in Fourier space. The turbulence cascades down. There is a region where things dissipate. And I'm not going to go into details of this, but maybe at larger scales, there are other physical processes that are relevant to actually give shape to the spectrum. Today, I'm not going to talk about in detail of how all of these processes happen. I just want to talk about a simple model that somehow parametrizes what we think is going on here and tries to give results similar to numerical simulations.
Are you trying to describe just the saturated state?
I'm just trying to talk about
approach to the saturated state.
In the end, what I care about is the saturated state. The model that we generate, I can come back to this in a second. Okay, so the idea is not to worry. The idea essentially is initially work in Fourier space, identify what are the scales that are relevant to the problem, and then go to real space, having identified this, and come up with a model that tries to incorporate the physics shown in this plot in a very simple way. Okay, and well, again, you don't need too many details about this. We know we can derive an equation, a formal equation for the transfer of angular momentum in terms of the mean of the stress. And of course, we could write, well, we know this is, we know what is behind the stress actually correlated fluctuations in the velocity field and the magnetic field. And in principle, the reason we cannot solve this problem in a closed form is because we do not, for the mean quantities, there are higher order correlations that enter into play. Of course, we could derive equations for these higher order correlations, but the problem is that there are higher and higher order correlations that enter into play. And what this is called is this is no other thing than the closure model, as you usually encounter in turbulent flows. So the idea is that for what we have right now is a very simple closure model for the stresses. Essentially, we call this different alpha times the pressure. What I want to do is to go a step beyond that and try to incorporate some of the physics I think are playing a role. I do not have time to make justice to previous models that people have worked along these lines without mean fields. There is a lot of work by Kato done in the early 90s. Gordon Ogilvy put forward a model very recently. I can just show you very briefly what are the main features of these models. Essentially, if you get scared, who is not going to get scared? Essentially, what you care to do is to write equations of motions for the stresses, for the higher order correlations. And there are three ingredients to this. One is what is the terms how things change in time? Essentially, you have times that drive the turbulence, for example, this term. You have terms that connect different components of the stress, what I call here the Sij tensor. So here this appears here, and it also appears here, okay? So there is driving, there is communication, and then there is saturation. These terms saturate the system here, and these are proportional to the magnetic energy, okay? So this is a general feature of these models. It's not hard to understand why you need this. Things grow, this growth spreads to other stress components, then you need to saturate the system. This is what I actually see. Again, this is similar in the model that Gordon Ogilvy put forward. And you can, the key point here is that you can, it's not only just making a model for this to make sense, but in this model, inevitably, you are going to have constants that you need to adjust using numerical simulations to be able to describe what is really going on. So these two models are models with with zero mean fields. We asked the following question: how does the MRI looks when I look at it in terms of the stresses? And the way you do this is very simple. You just write the equations for MHD. You define mean fields and fluctuations. You can write down equations for the temporal evolution of the fluctuations, and you can write down equations in terms of this for the temporal evolution of the stresses. When you do this with the MRI, you have naturally that even though we are trying to find equations that describe the Reynolds stress and the Maxwell stress, there is a new type of correlation that appears inevitably for the MRI. In the previous two models, the models were closed using just also the Reynolds stress and the Maxwell stress. What I'm saying here is that when you have a mean field, things are such that there is a new correlation that appears coupling the system of equations. So this is playing the role of communicating the growth essentially of the Reynolds stress to the Maxwell stress. Because this happens, you actually are forced to introduce dynamical equations for this new correlation again. Here I'm just going to show a few equations. This is actually a system of 10 equations. And what you see here is that now the system is highly coupled. This just describes exactly the linear growth of the MRI. What we have done is to use this to, as a model for the pumping that the MRI would produce in the nonlinear regime. And to accomplish this, we have modeled these scales that appear naturally in the problem. This is just a mean scale weighted by the power spectrum of the stresses. I'm not going to go into the details, but this essentially what I need you to understand, to know now, is that with this model, where this scale is proportional to the mode that is growing the fastest in the MRI, this quantity is the only other quantity that enters this set of equations that is going to influence the ratio between the different stresses. Here, kappa is the bicyclic frequency, Q is just a shear. So if this were set to 0, the other quantity that dominates the ratio of the stresses is just a shear. Now with this scale, this is also going to play a role here. Well, no. Well, this is a simple model. There are different scales that appear that depend on two indices. For simplicity, we set all of them equal. Okay?
Kmax depends on time, because it depends on what D is doing.
Yes, this is yes. So essentially, if you want to think about this is what you want to accomplish in the nonlinear regime, and you are saying that it's a fraction of what you know from the linear regime.
But if I started out with beta 10 to the 20, then Kmax would be absolutely enormous. But that would have nothing to do with the non-DSF.
Yes, because, yes, that's a good point. The thing here is that when you take the mean value of the stresses, you have a sum over Fourier modes, okay? So what I'm saying essentially is now, and this sum has been done essentially starting from k equals 1. So the k equal, if you are driving this for a k that is much, much more than that, you lose this. That's not something incorporated in the model. You have a sum over modes. You are saying if my mode is smaller than k equals 1, then it should not contribute, right? So what we are doing here is that, and this is the same that you know from the simulations. If you just were to set the magnetic field too strong, you could not be driving the MRI.
I was actually saying the opposite.
Oh, sorry.
Weak field,
yes.
The growth is initially on extremely small scale.
Yes.
But that doesn't have anything to do, the memory of that k is lost later during the evolution. So I think you don't want k to, anything to do with the initial.
Yeah. No expression is a conceptual. This is a time-dependent system.
Yeah.
And Kmax is a function of time, but it looks like you're using it as though Kmax is some well-defined value.
Yes, well, this is what I was going to, what Ellie was pointing out before is, what we're actually trying to do is to accomplish is to see if we can describe, if this system of equations can describe the saturation of the MRI. Because the linear regime of this, let me say it this way. This system of equations, if I set this parameter to 1, okay, and all of these are Kmax, this is exactly the linear growth of the MRI described in terms of stresses, okay? And here it would not matter how small is your magnetic field, because essentially, okay, this is a point. Essentially, the magnetic field here has been scaled out of the problem by defining k times b. So this is what you were saying. So this will grow in any case, okay? Now, you might not be able to resolve this in a simulation, but this will be growing, okay? So by what the idea here is, we want to describe what is going on in the saturated regime, is to propose a model to say, well, that the scales that enter into the problem can be parameterized like this, and we will see if this is a good idea or not. So this is going to describe the exponential growth of the MRI, but this has to stop somewhere. So you need a model to tell you when this should stop. And the idea is you see how this will work, because when the stresses are growing, the magnetic energy is growing, and these terms essentially are higher order correlations, if you want to think about it as triple order correlations, that are going to quench the growth of this, okay? So essentially, I have a model that depends on 2 parameters. If you don't want to think out the scale, that's fine. This is the idea that we came up with. But this parameter here, what essentially does is control the ratio of the stresses at saturation. And this is going to tell you what is the absolute level at which the stresses saturate, okay? Say that again. Everything is dimensionless. Yes, because in the linear regime, you can show actually that that correlation is identical to the one that I show, and we have actually just saying this. So W can be defined this way, or you can actually define as correlations in the vorticity and the magnetic field. This is a current.
Yeah, not length field.
No. Yes. So that's what I was trying to say before.
Not simple cross resistance.
No. No. This is a different kind. This is, again, you just do the linear analysis of the MRI. This shows up, naturally. It's not something we put by hand. Okay. And we actually, so this is a good point. Well, I'm now claiming that it's a new quantity that needs to be introduced for these models to do their job. Is this quantity really important? So what we did was to just use the publicly available version of SUS. This is a random we did with Maxwell random stresses. And when you actually calculate this correlation, this is at the level of both stresses. So somehow it might not be, yes?
Is M naught, is it something that we have to introduce into the, you can calculate it within your theory?
No, M naught essentially appears because it's a natural scale in the problem, and there is one parameter that is going to tell you that you have to adjust in order to be able to recover the level of the stress at saturation in the nonlinear regime.
You have to adjust using the simulations.
Yes.
You cannot calculate it.
No. But, well, not yet.
All right.
Okay. So the point I want to make here is very simple, is that this quantity W that I said appears natural in the equations is dynamically important. I know of other correlations, the velocity and the vorticity, that are naturally not important in MRI simulations. Okay, so this is getting back to what Dimitri was saying. Essentially, I show you I have a system of 10 equations that are nonlinear that I claim I can model essentially the driving of the turbulence on the one hand and the saturation of the turbulence on the other hand, and I can use numerical simulations to calibrate these 2 parameters. So when these 2 parameters are calibrated with available numerical simulations, this is what you find, is that you can describe actually all of the most important correlations that we know from the numerical simulations. And this is not a minor point, because if you were to walk along this line, alpha parameter that has played the astrophysical community on accretion disk varies by several orders of magnitude. The 2 parameters that I have in this model, once those 2 values are adjusted, you can describe the correlations that you see in dynamical simulations in a wide range of the physical parameters. So this is essentially what is M naught was before. And when that parameter I showed before is set to certain value that depends on the numerical simulations, then the saturation of the model gives you this. Okay? I have a linear of nonlinear existence of 10 nonlinear equations where the stresses are the dynamical variables. I have two parameters in the model. One controls the ratio of stresses. The other one controls the level at which things saturate. I have numerical simulations available. I can plot those, and I can adjust the parameters in my model that give you this. Okay? I mean, this, the model was built to do this, right? That's the point. This is not going to explain what is going on in numerical simulations. This is a smart way to parameterize what has taken a lot of work to find out, and maybe include this in global models of accretion disks. Okay? In the way of doing this, we have learned to ask different questions from what we have been asking for many years. For example, this quantity W is dynamically important. Okay? Something else that we have done, all of this has been calibrated with Keplerian disks. So essentially, in an alpha model, you know exactly what is the prediction for how the stress should behave as a function of shear. It should be linear on shear, and you should have negative stresses for negative shear. Okay? In the model that I have two free parameters I already adjust with Keplerian disks. So I can crank now the shear parameter and see what happens. Okay? Before doing that, we actually run a set of numerical simulations to see what was the behavior of the stresses in the nonlinear regime with Zeus. Okay? This part, I don't know if you are surprised or not, is not linear on the shear. And this means that you do not have transport for negative shear. Of course, the MRI is not active in the linear regime. But a priori, you didn't know whether there were some nonlinear instabilities that would produce negative transport. Our claim is that that is not the case. We ran Zeus to show this. What? Yes, of course, yes. Because because you have an alpha model, you can adjust always alpha to match this somewhere. So we on purpose chose to match this on the Keplerian case to see, because this is pinned down here and this is pinned down here, right? So this is not linear, that's a claim, okay? Now the question is, I have already adjusted two parameters that I have in the Keplerian case. What happens when I solve my system of equations and study the evolved state of the system for different values of the shear? And you get this, okay? Again, this has been pinned down here, and there is no need to pin it down here because this actually produces zero stress for negative shear. Okay, so my claim is now that you have a simple model. Well, let's see, quote unquote, simple model for the evolution of the stresses that would give you in the saturated state the same result that you get with the numerical simulations. This
model applies for shearing on an outer mean magnetic field.
No, because as you can see here, this is set in. Yes.
But don't the results depend upon the initial field condition, the initial field strength chosen?
That's the point. That's the point. That the amount of magnetic energy that you get.
I'm looking at the shear here.
No. But no, because now you have to leave everything constant and just change the shear. Right?
Okay.
That's what I want to study.
Is there a single essential piece to the model that gives this nonlinear behavior?
We can talk about this. I don't know. Just asking if I take away a 10 and get the same behavior. I would say no, but we can talk about it. Okay. So this is what we stood a year ago, essentially. As you all know, this was built with the mindset of describing numerical simulations that are done in the ideal MHD regime. The question is, well, if this makes any sense, how this correlates what we are learning now about the dependencies of magnetic prime number and resistivity and viscosity. Essentially, well, I should have said something else here. So this is what Steve was saying, that I mean, this model does parameterize correctly the linear behavior that we know of the saturated stress in terms of the magnetic field. Lambda MRI, as you know, is proportional to BC, so this is linearly proportional. This dependence, I'm not going to go into all of these issues now. We do not understand yet. And this thing here is, well, if I start decreasing and decreasing the magnetic field, at some point I'm going to find the same value of the stresses that I get for zero net flux simulations. But this, whether this is artificial or not, that will lead you to Sebastian to discuss this, but essentially I can't reach that point. The question is whether this is physical or not. I can crank down the magnetic field in my model until I reach this saturation. The question is, do you really want to do that? So that's up for discussion. Okay, so now I'm victim of my own idea of these 20 and 25 minutes. I just want to show you the progress that we have been making in the two ends of this problem. One is how you pump things at a given scale, and the other one is how you kill things once they have grown exponentially. And this is a paper that I published recently with Chiquan Chan. Essentially, and I'm not claiming we have done all of this for the first time ever. A lot of people have looked at various different limits of the MRI with viscosity and resistivity. What we did was to just take the incompressible case, the simplest case possible for the magnetic field in the vertical direction, and essentially beat the problem to death. We have undertaken a very extensive parametric study, and what I take from this is the following, is that no matter what is the Reynolds number, not matter. You can actually divide the whole parameter space into two regions. One is the ideal MHD behavior, something you can call resistive and something you can call viscous. The point that I want to make here is that I think this result is new. I don't recall seeing it in the literature, how things behave at very high magnetic Prandtl number. And I know that most people have looked at this problem essentially in this asymptotic regime with zero viscosity. The point that I want to make here is that this behavior actually holds down up to magnetic Prandtl number of order 1. I'm not sure this has been appreciated before. I'm not going to go into this. So this is going to be just towards what I have been doing with Jeremy. So in the ideal MHD regime, we have solved the exact problem for the linear modes of the MRI with the vertical magnetic field. Okay, those modes look in physical space like this. The velocity field is a sine in the vertical direction, and the magnetic field is a cosine in the vertical direction. Okay, in the ideal MHD case, you can actually make a projection in the midplane of the disk, so this would look like this. Okay, and these two angles in ideal MHD are respectively 3 pi over 4 and pi over 4. So MRI modes, which are exact modes, exact solutions to the equations in incompressible MHD, have velocity and magnetic field components that are orthogonal to each other. Okay. Yes, this is for the well. Yes, VC only, KC only, and what the plots I'm going to show are for the mode that is growing the fastest. Okay. So the point I want to make is that we have studied how these structures, how these modes behave as a function of viscosity and resistivity. Okay? And what we have found is that the physical appearance in physical space, you should be able to see this in your simulations if you put the value of viscosity and resistivity, changes. For magnetic Prandtl number of equal unity, you increase the Reynolds, you decrease the Reynolds and magnetic Reynolds number, and this is going to go to a symmetrical direction, this to the radial one, in this way. Okay? Now, why am I bringing this up? Essentially, today we think one of the most promising mechanisms to produce a saturation of the MRI are these parasitic instabilities. These are secondary, faster growing instabilities that can actually destroy the primary MRI modes that we are all used to. So what Jeremy did in '94, today with Shu, was to study what are the stability properties of this when you perturb this with weight numbers that are actually in our horizontal planes. So why is this important? Well, essentially, for a given mode, parasitic mode, the background that these modes are seeing is going to change as a function of the Reynolds number and the magnetic Reynolds number. I don't want to fool you. It's not just that the background is changing. The whole character of the problem changes. The equation that you're solving changes. But it's an intuitive way to see why this should matter for the development of parasitic instabilities. And I agree to, okay, so how much things change? Well, this is a picture of how the structure of these primary modes, the fastest growing, change as a function of Reynolds and magnetic Reynolds number. Okay? So I have equations to, this is not just a neat plot. I have equations to describe how these angles behave. I can describe this for arbitrary values of viscosity and resistivity. With that, I can actually study what happens with parasitic instabilities if I choose, for example, a given magnetic Reynolds number and I vary the Reynolds number. Okay? So these are preliminary results with what I have been doing with Jeremy. And essentially, we have generalized a study that Jeremy did in '94. This is a result for ideal MHD. And these are parasitic modes when I keep the magnetic Reynolds number and I bring down the magnetic Planck number, essentially, well, yeah, no, I don't bring it down. It's, it goes from a very small number to a large value of PM. This goes from 0.1 to 50. So we have also studied other types of parasitic instabilities that show up into the problem. I'm not going to go into details unless you ask me. But there is one point to be made here, having said that these are preliminary results. The fact is that parasitic instabilities seem to be weaker with higher magnetic Planck numbers. Now, this is not yet an explanation, but it's worth exploring this. Is this a hint for the difficulties to drive the MRI at low PM? Because if I have high Planck numbers, essentially, I can kill the parasitic instabilities, then it might be easier to drive the turbulence. At low magnetic Planck numbers, the parasitic instabilities are very active. It might be harder to keep the turbulence going. So the final question that I will leave now, and maybe we can talk in a few months, is whether the destruction of primary modes by parasitic instabilities as a function of Reynolds numbers and magnetic Planck number have something to say about the dependencies that we have seen in the nonlinear regime with simulations. Thanks so much. I agree. Yeah, honestly, this is the beginning of an analytic study, and we will pursue this on numerical grounds. But this certainly seems to be there. I mean, and these instabilities should show up. If it is parasitic instabilities where it's actually killing these primary MRI modes in simulations, they should show up. This is a linear study, so things should be present there. The other option, I have not looked into that. I can only give you the answer based on what I know about the linear regime. In the linear regime, what you know is that both numbers, well, no, okay, I understand your point. Give me 1 second. So this is this is a linear calculation. So I'm sorry. These are ratios. You can look at the scale. This is just the amplitude, so the scale is not really relevant. But essentially, what you can see here, the solid line is for magnetic Planck number equals 1. Okay, so you can get the same level of stresses no matter what is the magnetic Planck number if your Reynolds number is large enough. So this is PM equals 1, right? So no matter whether PM is much larger than 1 or much smaller than 1, I'm going to reach at some point in the linear regime, not necessarily in the nonlinear regime, I don't know the answer to this. In the linear regime, I should be able to do exactly the same by increasing further the Reynolds number.
So it's basically saying that if you go to a weak enough viscosity and resistivity, it really doesn't matter.
For the linear dispersion relation, it doesn't matter, but for the turbulent cascade, it may matter a great deal.
Might matter, yeah, that's a different question. This is a linear instability, right? I answered that. Yeah.
Oh, sorry.
And is the parasitic modes is the same statement. So it's the statement at low Reynolds or magnetic Reynolds, you see a Prandtl movement. Not as RE goes to infinity, you see a Prandtl movement.
For the parasitic modes, I'm not in the position of commenting much further than what I said.
I was asking what you said.
Oh, no. What I said was the linear regime for the primary modes, okay, for the MRI.
Modes are modes taken not as RE goes to infinity, but as Reynolds number of order 1.
No. Give me 1 second. So these sketches are all for the primary modes, right? And the primary modes are where I'm going to set the background over which are going to perturb to see secondary faster growing instabilities. Okay? So there is, okay? This is the primary mode. For the primary mode, you can study the dependence on magnetic Reynolds number and Reynolds number. It looks like this, okay? So for the parasitic instabilities, I can tell you only this. If I keep the magnetic Reynolds number as the order of 100, and I increase the magnetic Prandtl number from 0.1 to 50, I get this. What I said I cannot comment anymore is that I don't know much more. This is the